I'm ready to do it. All right, good afternoon, everyone. I hope you're all doing well as the semester winds down and as many of us start to prepare for Easter. Thanks for joining us for the last Arts and Sciences Professorial of the year, not the last Professorial of the year. Our lecturer, Sammy, I think you're still up. So no pressure, but you'll have to top this one. So, all right. Well, just for the room.
Yeah, for the room.
Switch. Oh, it's under the. Oh, very good. All right. Well, today I have the honor of introducing another of our remarkable colleagues, Laura Pudwell from the Department of Mathematics and Statistics. Like many of you, I'm eager to learn about the joy of enumeration. Although there was just a form about enumeration, wasn't there? Is that? But before I turn the podium over to Laura, let me share with you the many accomplishments that led to her promotion. Laura submitted a clean, polished, and extraordinarily articulate application. As a Valpo alumna, she very skillfully addressed her fit with our mission, making it clear that she put students first in her work. Reviewers found her to be very well aligned with our mission and campus ethos. Laura most definitely exemplified the teacher-scholar ideal for our faculty. The tenure and promotion summary review described her as an exemplary teacher who focuses heavily on student engagement in her classes. Student reviews of her courses have been excellent, with abundant praise for her skill, enthusiasm, and patience. She also demonstrated clear leadership in promoting and mentoring undergraduate research, which we'll come back to in a moment. Groups both on and off campus have recognized Laura's teaching and mentoring through several different awards. For example, in 2014, she won the Henry L. Alder Award for Distinguished Teaching in Mathematics, one of only 3 recipients nationally that year. And in 2017, the International Honor Society for Key Women Educators selected Laura for its Woman of Distinction Award. But as good as she is in the classroom, Laura may be an even better scholar. Her departmental review described her scholarly record simply as remarkable. At the time of her promotion application, she had published 20 peer-reviewed papers since her promotion to associate professor, and many of her projects included faculty co-authors or student collaborators. She also secured more than $500,000 in research funds during that same time frame. Laura's external reviewer complimented her work on several fronts. The reviewer, noting that 10 of her published papers had included undergraduate co-authors, stated, quote, "This is an outstanding record for an individual faculty member at any rank, and I know of few faculty nationally with comparable accomplishments," end quote. That reviewer further described her scholarly accomplishments as substantial and considered her full publication record as outstanding, even for a faculty member at the rank of professor. Laura's records in professional development and campus citizenship were also exceptional. She has been a regular conference attendee and presenter, and she has served as a manuscript reviewer for several journals. Her departmental review noted the significant work she performed as vice chair and then chair of the Indiana section of the Mathematical Association of America. In 2020, she also planned and hosted a virtual conference for the International Conference on Permutation Patterns. She's even served as an external reviewer for 2 PhD theses. She has been a model citizen in her academic discipline. On campus, she has served principally through the Committee on Creative Work and Research, with notable leadership as chair of that committee. But she has also been active in Greek life as faculty advisor and then chapter advisory board chair to the Phi Delta Theta fraternity. Her departmental colleagues lauded her as a great departmental citizen, regularly willing to take on ad hoc assignments beyond her regular duties. Multiple reviewers described Laura's application as outstanding in all areas. This led to effusive, enthusiastic endorsements for her promotion. And her external reviewer stated bluntly that, quote, "Professor Pudwell's accomplishments and professional development richly merit her promotion to the rank of professor." The provost agreed. So please help me congratulate Laura Pudwell on her well-deserved promotion to professor.
John, thank you for that kind introduction. It actually makes me tired to hear all the things I do at once because they're usually so spread out. And for all of you for showing up today, thank you so much for being here. It's really great to celebrate this milestone among so many friends. So the job here is to tell you about my research. And the one sentence version is, I count abstract math objects. And if you haven't talked with me about that before, I'm guessing you already have two questions. Like number one, you learned to count when you were in kindergarten. How did I get a PhD in counting? And number two, what are these abstract math objects? So those are the first two questions I'm gonna try to address. You can't actually see in the room, but the first title here says, what is counting? The second says, these are a few of my favorite things. That's how I'll address those two questions. Then at the end, I'm gonna try to zoom out a little bit and give you a sense of what I see as the kind of unifying thread in all my work. If you're worried about technical details in a math talk, I will assure you those are basically in the references at the end. So this is really pictures and stories where if I do my job well and you're not a mathematician, I hope I broaden your view a little bit of what math in action looks like. So let's start with what in the world is counting as research. I am guessing that when you picture counting, you probably picture things like this. When you first start to count, you probably count on your fingers, although you might have put a calculator there instead of an abacus. But to give you an insight into me, when I was a high school senior in AP Calculus, there was a whole grading period where I brought an abacus to class instead of a calculator because I had just read a book on how to use an abacus and I wanted to see if I could use it faster than my friends could type the same things into their calculators. True story. And I'm out of practice now, so don't race me an abacus, but if that's the kind of student I was in high school, then it's maybe not so surprising I went on to college and declared a math major. And when you're a math major who enjoys structure and had a great time being a math major, kind of makes sense that the next thing is to go get a PhD in math. And so my career path has been pretty linear, where I'm in one chapter of life and go, that was fun. How do I do more? And I go to the next thing, and that's kind of led me to where I am today. But my counting tools don't look like that anymore. Instead, when I picture counting, I picture things like this. So the thing on the right here is what's called a generating function. It goes with one of the stories later in this talk, but you need some calc too to understand how to unravel it. And this thing on the left is just a screenshot of software I use often in my work. So in grad school, when I was at Rutgers University, I met Daron Zeilberger, who is famous or infamous, depending who you talk to, on the appropriate role of computers in math. So he thinks one day computers will be doing all the math. He is very pro using computers to figure out math. He was my PhD advisor. So my research was writing a family of algorithms to solve a family of counting problems and then proving that the algorithms did what I said they did. So that's kind of my backstory on what is counting as research. When I talk about counting, I don't mean I'm lining things up and going 1, 2, 3. I mean, I'm really trying to take a deep dive into structure to answer how many of something there are in a more efficient way than counting on your fingers. So I'm interested in questions of how many. I'm not interested necessarily in doing a party trick fast, but I am interested in counting. So what do I count? To get a hint, here's kind of the more recent end of my CV and a poster from a talk I gave last summer. And what you should notice is that there's 3 words that show up over and over and over, and they are permutation, pattern, and avoid. And so to give you any sense of my research, I need you to have working definitions of those 3 words. And so I'm going to take them, I think in the order I just said them, permutation first, then pattern, then avoid. So first, what is a permutation? A permutation is just a list where order matters. You could make permutations of people or of letters. I make permutations of numbers. And I look at permutations of the numbers 1 up to n with no repeats. So just to get some concrete examples up here, how many ways can you put one thing in order? Just one, it's right there. How many ways can you put 2 things in order? Okay, yeah, the Phi adults are helping me out. There are 2. Number 1 goes first or number 2 goes first. Those are the 2 ways to put 2 things in order. How many ways can you put 3 things in order? Okay, 6, right, because you have 3 choices for what comes first. And as soon as you know what comes first, you have 2 choices for what comes second. And how does this scale up? These numbers get big kind of fast, but the way we just talked through that tells you how many permutations there are of n things. You have n choices for what comes first, and one fewer choice for what comes second, and one fewer choice for what comes third. And the abbreviation for that multiplication is n factorial. That's how you read the exclamation point. Now, the thing about permutations is, if you walk up to a random not mathematician and say, what do you know about permutations? They either say, what is that word? Or this slide is everything they know. So it might not seem like I have much to count because I already told you how many permutations there are, but this is just one point of view. So let me show you a different point of view on these same objects. A permutation is still a list, but when I see the permutations of length 3, I'm actually picturing these diagrams. So a permutation of length 3, its diagram has 3 dots, and the heights of the dots match the numbers in the permutation. So for example, 1, 2, 3 has a dot at height 1, then a dot at height 2, then a dot at height 3, all going uphill. Or 1, 3, 2 has a dot at height 1, then a big dot at height 3, then a medium-sized dot at height 2. The heights correspond to the numbers in the permutation. Different point of view. To make sure it really makes sense, let's look at a big one. Here's a permutation of length 9, and again, you can track the heights of the dots match the numbers that you see in the permutation. So 5, then 6, then 2, and so on. When I think of permutations, yeah, it's a list, but this is how I'm visualizing the lists. That's word number 1, permutation. But looking at 9 dots at once is kind of a lot, so let's focus on just some of them, and notice how 3 of them just turned orange. Yeah, they turned orange in here too, that's good. I'm going to focus just on the 3 orange dots and completely ignore the rows and the columns with black dots. So in your mind, just completely erase these first 2 columns and then these 3 here that have black dots and erase the last column. Same thing, erase the rows with black dots. And what survives if you only look at the orange dots is a small dot followed by a large dot followed by a medium dot. So the orange dots, even though they're spread out inside of the bigger permutation, they make the same shape as 1, 3, 2 did on the previous slide. So there's our second vocab word, a littler permutation inside of a bigger one. That's what's known as a pattern. And so there are lots of 1, 3, 2s in here, not just the orange one. I could have taken the first 2 orange dots and then this one right here. That's also a 1, 3, 2. The 3 at the top here are 1, 3, 2, but 3 dots that make that shape somehow spread out in the permutation. That's a 1, 3, 2 pattern. There are lots of other patterns in here. So if you look at the blue dots, notice they're in order from smallest to largest. That's a 1, 2, 3, 4 pattern. And so that's what it means to contain a pattern. The opposite of contain is avoid. No matter how hard you look for 4 dots in here, you will not find 4 that go all in decreasing order. And so that's my last vocab word. If you're looking for a pattern and can't find it, then you've avoided that pattern. Now you have all the vocab words, I can tell you a research question. If I just say, here's 2 permutations, does the big one contain the small one, yes or no? That's a great homework exercise. But the research question that kind of drives my field is this. Let's say you have a particular pattern in mind, and you think about bigger and bigger permutations that have to have that permutation inside of them. You could ask how many permutations of size n have to have pattern P inside of them. Or you could ask how many permutations of size n avoid P. These are really 2 versions of asking the same question because every permutation of length n either contains P or avoids P. And we already saw there are n factorial permutations of length n. So those 2 questions have to add up to n factorial. But you can fill in what pattern you're looking for with all kinds of different things. How many permutations avoid 1, 3, 2? That's been figured out. How many permutations avoid 1, 2, 3, 4? That's been figured out. How many permutations avoid 1, 3, 2, 4? Mystery. So you've already heard your first open problem of the talk based on knowing 3 definitions. And if you're more into other fields or driven by applications, you might still be wondering, well, why are people avoiding permutations? I can answer that too. The motivation comes from computer science. So if you've ever opened a spreadsheet, you've seen this button, which you can just trust sorts the data that you've highlighted. And if you're just using a spreadsheet, you're happy that Excel or Google Sheets does that for you. But if you've studied computer science, you realize there are dozens of sorting algorithms to choose from, and they all have different pros and cons. So I'm going to tell you about a specific sorting algorithm that's motivated by how you interact with a pile of books, which I'm convinced, even in the era of ebooks, you know how to interact with books. Let's say that pile is sitting on your desk and you get a new book and you want to add it to the pile and not make a mess. Where are you going to put the new book? On top, right? That's how you add it to your pile and not make a mess. And let's say you really need this book with the yellowed pages and you want to get it out of the pile without making a mess. What are you going to do? Okay, top down, right? You are not going to just take the corner of the book and yank it because you're going to make a mess, but you can one at a time remove the things that are above it until you get to the book you really want. So what I've just described there is kind of how a computer scientist might interact with a data structure called a stack. A stack is kind of an image for how computer memory works, where you can add new things to the top, or you can take existing things out of the top, but those are your only two legal moves. And a famous result in a classic computer science text from the 1960s is if you want to sort a permutation by just one run through a stack, you can sort it to be in increasing order if and only if it avoids 2, 3, 1. I won't go into more details of why that's true, but this is the motivation for why people started talking about pattern avoiding permutations. It was really a computer science sorting algorithm question, and avoiding 2, 3, 1 was useful language to talk about what could be sorted. So that's the computer science side of the story. So now where do mathematicians come in? Well, in pure mathematics, it's usually not about an application, it's about a motivation. And so there's this result in the 1960s that says that this definition of having a 2, 3, 1 pattern is a useful characterization for studying this sorting algorithm. Mathematicians see this and go, well, the definition of pattern makes sense if you replace 2, 3, 1 by a different permutation. What happens if I avoid 1, 3, 2? What happens if I avoid 1, 3, 2, 1? Name your favorite pattern. What happens? And so mathematicians who do theoretical work are kind of in the business of taking a result and trying to put it in a more general setting. And then when you do that, it's not just all abstract math. Cool things happen along the way. So in the last 30, 40 years, as people have answered this, what happens when I avoid this pattern? Cool things have happened that connect to computer science, biology, chemistry, statistical mechanics, and even geometry. There's all kinds of webs of connections between things just by going, someone defined permutation pattern. What happens when I avoid other things? So the theme you should have at this point, especially if you haven't thought about theoretical math research and what it looks like, is that mathematicians like me are studying structure for its own sake, but a lot of the time there's this bonus that something cool happens when you're in the middle of counting and studying a structure for its own sake. So that's my big picture on how is counting research, but I still probably have another follow-up question. If you have this picture that math is all already figured out, how am I coming up with new things to study? So that's the next section of the talk. I've picked 3 of my favorite research projects over the last decade or so that I've come up with in very different ways to illustrate where do new math structures come from. Bonus, part of why they're my favorites is because they have surprise connections along the way. So number one way you get problems when you're in grad school is you have a PhD advisor who says, here's a cool problem, why don't you look at that? And then you get to be faculty and you don't have an advisor doing that anymore. And so you have to work in different ways to find problems. Although sometimes you're lucky and someone still hands you a problem. So this is an email I got at the end of my first summer here at Valpo as faculty. In summer 2009, I get an email from a musician in Boston, and I will summarize it for you, but it's kind of comical. It says, hi, I'm helping my middle school age daughter with a math project. And we have this list of numbers, and I Googled it, and the only hit was this website, which seems to belong to you. Can you help? And that website, it says math.rutgers.edu. It's an output file from one of the algorithms from my PhD thesis. I was not doing a middle school math project in my thesis. Can I figure out what's going on? So you can handle hearing a middle school math project. Let me show you the problem this Harris family in Boston was looking at in summer 2009. They were piling cubes. So you can think of these cubes, they're made up of squares. Each square has an area of 1. And so if you talk about the surface area of this first cube here, it has 6 sides, its surface area is 6. And then here is the pattern they did. They took that cube and put it on top of a row of 3 cubes. What's the surface area of that shape? Well, it's still small enough you can count. There's 4 squares on the front and 4 squares on the back. And if you count around the top and sides and bottom, 10 more, surface area of this shape is 18. You take that shape and stick it on top of a row of 5 cubes, and you can count up what's the surface area of that, you get 34. This is the middle school math project. Why did they search and get my PhD thesis? Well, it turns out that the surface area of the nth shape that they were looking at, so the cube counts as shape number 1, and then the one on top of 3 counts as shape number 2, is the same as the number of lists with 2 1s, 2 2s, 2 3s, all the way up to 2 n plus 1s that avoid these 3 patterns. So you somehow are getting the same how many answer from their surface area problem as I did from one of my pattern avoidance problems that I wrote algorithms for in grad school. And to maybe make it a little more concrete, here's their second shape. We already counted it has surface area 18. Here are the 18 lists that have 2 1s, 2 2s, and 2 3s that avoid this triple of patterns. And the way that you explain it's actually the same is you find a way to associate each of these lists with one of the squares on the outside in a way that scales up. And so this is an example of I had solved a problem, someone else was solving a different problem. We realized the data matched up, and it's fun for me to figure out why does the data match up. So that's number 1 way to get a problem. Someone hands it to you, and that's fun. The second way I get problems is maybe a more canonical route, and it's by following the path in the literature. So I've already introduced you to this theorem, which kind of got my field of work started. Donald Knuth proved in the 1960s that if you want to run a permutation 1 time through a stack, you can sort it if and only if it avoids 2, 3, 1. A little more than a decade later, there's a result that if you want to sort your permutation through something related but slightly different called a pop stack, it can be sorted if it avoids this pair of patterns. Okay, so we have 1 time going through a stack, 1 time going through a pop stack. Then another decade later, you have a PhD thesis result that says what happens when you run 2 times through a stack? Well, then you have to get fancier and more self-referential with your patterns. This overline is on purpose. It means you avoid 3, 2, 4, 1 unless it's part of a 3, 5, 2, 4, 1. It's getting more complicated because you're going through the stack multiple times. But what's the missing kind of next step in the story? 1 time through a stack, 1 time through a pop stack, 2 times through a stack. What should somebody look at next? 2 times through a pop stack. And that's what my friend Rebecca Smith and I did several years ago, and you see how much more fun it got. But it's even better than that. All the theorems on the previous slide, someone had counted the permutations that were involved. So we know how many permutations avoid 2, 3, 1. We know how many permutations are sortable after 1 run through a pop stack. And so Rebecca and I also wondered how many permutations are sortable after 2 runs through a pop stack. And if you like counting, you don't have to know all the sequences. There's this amazing website database called the Online Encyclopedia of Integer Sequences. So we had actually figured out the formula that was that generating function on my first slide, and we could churn out numbers, but we wondered if they were related to anything else. We punched our counting sequence into this database, and it said, yeah, someone's seen that sequence before. Turns out it's the number of generalized dominoes. So domino usually has 2 squares. It can be vertical or horizontal. These examples have 3 squares, but that can be drawn on a twisted cylinder of width 3. So that's a cylinder. You see a helix going up the side. What I mean by width 3 is if you go 1, 2, 3 squares in a row, you're still kind of visiting new territory. As soon as you go 1, 2, 3, 4 steps in a row, you've gotten right above where you started. And the consequence of that is it makes some things count as the same polyomino, because like if I took these 4, this rightmost square is really on top of where I started. And polyominoes aren't just game pieces. Apparently they have applications in some subfields of chemistry and physics. And so we're answering a computer science problem. We do our counting. We realize the counting matches up with a completely different story of mathematics that has connections to other fields. So studying structure for its own sake, but fun happens along the way. So sometimes people give me problems. Sometimes I'm following the path in the literature. But my third example is kind of my favorite way to come up with problems. And I like to tinker. So if you deal with theoretical mathematics, there's a bazillion definitions, you know, and people haven't considered every possible mashup of those definitions. And so you might go, here's one definition, here's another, never seen them in the same paper. What happens when I mash them up? And this is my favorite story of that. So I've told you about permutations, but this is a special kind of permutation. A permutation is alternating if its digits go up, then down, then up, back and forth. When I gave a practice run of this to my brother, he said, what if they go down, then up, then down? Those are alternating too, but I like these ones for reasons you'll see in a minute. So you should check in your mind that you understand this definition of alternating. All of these go up, then down, then up as you read across. And I'm going to mash this up with the definition of pattern that I told you about in the intro. And I'm going to ask which of these alternating permutations has the most 1, 2, 3 patterns inside. Just tinkering, seeing what goes on. Well, these two on the right, they don't have 3 dots in increasing order, so they avoid 1, 2, 3. This one has 1, 1, 2, 3. It's right here with the 2, the 3, and the 4. This one has 1, 2, 3 using 1, 1, 2, 3, using the 1, 2, and 3. This one actually has 2 1, 2, 3s. You can take the 1, the 3, and the 4, or you can take the 1, the 2, and the 4. So out of these examples, this one has the most 1, 2, 3s. So the question then is, as you scale up, which alternating permutation of size n has the most 1, 2, 3s? And the general picture is this. It needs to be alternating. So notice this goes up, then down, then up, then down. But every time it goes up higher than all the previous digits. And every time it goes down just barely, because I want it to be going as uphill as it can. And so then the follow-up question is, how many 1, 2, 3s are in this kind of structure? Well, here's what it looks like for 4, 5, 6, and 7 dots. We already looked at the 4 dot version. It has 2 1, 2, 3s. Here's the 5 dot version. It has 4 1, 2, 3s. And I'm looking for the right department to recognize this sequence. So if Chris Eisman were here, he'd be super excited right now, but he's already been reading this paper. So this sequence, these are all even numbers. I'm wondering what's going on with them. They look very clean, very nice. And so I asked my favorite database. And when you punch some of this data into the online encyclopedia of integer sequences, the first hit you get is all chemistry words and no math. And then you search for some more terms and it's still chemistry words, but a little bit of math. So maybe bookmark in your head for a moment, 4, 12, 20, 38, as I go to the next slide. Where do you see 4, 12, 20, and 38? Somewhere that makes chemists happy. So 4, 12, 20, 38, the numbers I'm getting, the 2 is over here out of the way, but all the other numbers are the numbers in this second column of the periodic table. And I'll be honest, the last chemistry class I took was Chem 111 with Tom Goyne when I was a VU freshman, so it's been a while. But here's the high school or early college understanding of what's going on with these numbers. Each of these numbers is the number of protons you expect to be in the nucleus of an atom of one of these elements, and therefore it's the number of electrons you expect buzzing around the outside. And the periodic table has rows, the sizes it does, because electrons kind of live in layers or shells. And so the things over here in column 18 have their outermost shell at capacity. And the ones that we're looking at here have 2 bonus electrons in a layer beyond that. And so I was wondering, why are the shells the sizes they are? And I talked to several chemist friends and borrowed a PChem book and learned that there is a model for describing where electrons are likely to be called quantum numbers. And each electron can be associated with 4 integers. And you can really take those 4 integers and use them as the address for where a 1, 2, 3 is inside of my big zigzaggy alternating permutation. So there is a structural connection here, which I find wild and super delightful. So that is 3 different ways that I come up with new math structures to study and some of the bonus plot twists along the way. And that's just 3 stories of many. I had like 40 projects to choose from, and so I picked 3 of my favorites. I'm not going to tell you about all of these because I want to save room for the last chapter of the talk. But what I will say is all 8 of these pictures represent projects I have loved working on. 3 of them aren't even about permutations. One of them has the funniest backstory of any of my papers. So if you need something to ask in the Q&A, ask about that. And the last 2 represent current works in progress I'm pretty excited about. But instead of just giving you more and more projects, I'm exactly on time. I'm going to use the last 15 minutes here to try to tell you what I see as the common thread throughout all my work. Because if you look at it in this form, I picked 3 projects that have similar definitions to use, but my work is actually very varied. So some mathematicians might say the common thread in their work is, here's this big math goal I have, and here are how all my projects are kind of incremental steps along the way. My work is not organized like that at all. But I think I can explain the common thread in my work if I tell you more about my motivation for why I find counting abstract math objects a fulfilling and exciting way to spend my academic time. So there are 3 main threads in my personal motivation that I think I've only given you evidence of one of them so far. I think this stuff is beautiful. So when I'm going to count one problem and I realize it has a connection to something else, there's really a delight in the surprise connections. And there's really kind of an aesthetic sense of what's going on that I hope is what I've been communicating in the middle section of the talk. And so maybe the analogy here is how someone feels when they experience a great work of art or a great piece of music. There's also a sense of mathematical beauty going on, and that keeps me wanting to do more counting. Reason number 2 I do math is what I promised to keep in the references, but I'll talk big picture. Mathematicians don't just go, isn't that cool? Maybe the periodic table is involved here. We actually write rigorous proofs about why things work as they do. And if you kind of cringe when I say the word proof, I'll tell you that's actually one of the highlights for me. And the analogy here might be, imagine you've just started running and training and you finish your first marathon. How do you feel at the end when you've worked hard for something? If you talk to any of my friends who interact with me after I've proved something that I've been stuck on for months or years, it's a pretty fantastic natural high. And so this search for understanding why things are true also keeps me at it. But that's just 2 of 3 pieces. And I think the last piece maybe defies stereotypes about mathematicians. So I'm going to say the most about it. I do it for the sense of community. So I love looking for mathematically beautiful things and mathematically true things, but I also enjoy exploring these things with others. And to illustrate that, it's not just I give talks and I expect an audience to show up, although that happens. This is a pie chart of my papers since becoming faculty. And the most important feature is the blue part, the solo authored works, is only about 20%. The other 80% either has student co-authors or more likely mathematicians at other universities. And so when I'm thinking about a math problem, it's not this like solitary pursuit. There is literally someone else thinking about the same problem at the same time and regularly in communication with me about it. And I think that still doesn't say the community part strong enough. So I'm going to give it one more go before I move forward to some more pictures. When I was early career, like grad student and assistant professor, this whole publish or perish mantra is really drilled in. And so I had my next few research projects lined up, and showing up to certain communities was a resource for making progress on them. At some point in the last decade, the content and the role of the people have swapped places. And so my focus is really on participating well in certain communities, and then my research happens because of that. And so it's super weird for me to give a talk about my research and only talk about the content and not acknowledge the communities that affect how I think about it. And so this last 15 minutes, I'm going to highlight 3 communities that have loomed really large in my professional life in the last decade. Community number 1 is who you talk to if you like pattern avoiding permutations. It is the International Conference on Pattern Avoiding Permutations. Here we are the last time we could be in one place in 2019 in Switzerland. And you can look for the Lara in this picture, but what's even cooler is kind of the variety of experience levels in the room. There are regularly grad students who are at this conference for the first time. There are people of all kind of trajectories of career that are in and out depending on where the conference is located and what their schedule's like. And then there's a core of people like me who came once, loved it so much, and have been there every year since. So I have been to this conference every year since 2006, and it's not that those groups kind of isolate by age. We all get along and interact super well. There are some research areas that are really competitive and kind of mean. This is not one. I love hanging out with these people. So as I said, I've attended this every year since 2006. That means I've attended it everywhere where there is a red pin. And I've been on the steering committee since 2012, which makes sure we have new locations lined up. And since I'm one of 2 Americans on the steering committee, it means I apply to a National Science Foundation grant every time that we need more grant money to fund early career people to participate. This has been a huge part of my professional life. And as John mentioned in the intro, we were supposed to be in Valpo in 2020, and you know what happened in 2020. So here I am excited to welcome my research community, and I've laid all this groundwork, and then I became one of the first faculty on campus to have a Zoom account so I could host an international conference from my couch. But what's really cool about this picture is when we said turn on your cameras so we can get a conference photo, and this was when Zoom limited you to 25 headshots, this picture has people logged in simultaneously from 4 continents. And in the course of the 2 days run on Central Time, people logged in from 13 time zones, which tells me I'm not the only one that values this community. And all that work in 2019 and 2020 didn't go to waste. They'll be here in 2 months and I can't wait. So that is community number 1 that I credit with keeping me in tune with the mainstream of what's going on with permutation research. It is a place that has inspired so much of my projects content-wise, and it's been a place for me to find some really awesome collaborators. I would not have my research where it is today without this community. Community number 2 fits really well with the teacher-scholar model at Valpo, and it's this. So this is obviously not faculty Laura. This is senior year of college Laura with a faculty member that you might recognize who loves this picture. And I have to say that undergraduate research was hands down one of the most transformational things I did as a student. It was the first time I realized there were math problems that didn't just have an answer in the back of the book, and that it's actually a creative discipline. So I worked for 4 years with Rick. I worked for a year with Shoshana. I did a summer research project at another university. It's really formational for who I am today. And so I've spent a lot of my time as a faculty member working with students on undergraduate research because I understand the impact that that has on just getting a different sense of the discipline than you do in a classroom. So these are all the students I've worked with in 14 years on being a faculty member. Half of them are Valpo students who took on a project for an academic year, but half of them are students who came here for a special program called VIRUM, which is a mouthful, but it's the Valparaiso Experience in Research by Undergraduate Mathematicians. This program was actually founded by Rick and Jujana while I was a grad student, and they got a grant from the National Science Foundation for 3 years. It brought 9 students per summer to work in small groups on research projects with local faculty. And there was a whole professional development piece. They had a visiting mathematician each week. They had field trips to graduate schools. Just like the poster here says, it's meant to give them a kind of well-rounded experience to explore their future in math. The first VIRUM grant wound down about the time I joined the faculty. And so Rick invited me to write the second grant with him and then went off to be an administrator and left me, early career faculty, in charge. And so when that grant wound down, then I wrote a grant with Jujana to run it for another 3 years. When that grant wound down, I wrote another grant with Alex Capaldi to run it for another 3 years. A decade of my life was devoted to this program. Not running a project myself every summer, but for most of the summers in a decade, I ran summer projects with VIRUM and I helped think about the logistics of this program. And so it's been a big professional commitment for me too. And there's a few different cool outcomes that come from this kind of get to experience math outside of the classroom kind of program. So some students, like I chose this poster because of this cohort in particular, many of them do go on to PhDs in math, computer science, or statistics. And I think this group here from summer 2011 set the record for that. And it's so awesome to run into them now professionally as colleagues. There are other students who went straight into math or computer science jobs straight after college. And I see them less often at conferences, but it's still really fun to track. And there's still others who say, I really enjoyed my project. I met cool people. I can do math. I want to do something else. And I say, that's awesome. I need people who are unafraid of math in all careers in life. So that's a variety of things that can come out of it. But what they all had in common was they had a summer where they actually got to try working on something open-ended and see how it fits. And so this is the community I credit with helping me think very hard about the accessibility of mathematics. There are problems where you need to devote months and years to get the background to make a contribution. But I feel like spending so much time with VRM and with local students has made me think really hard about how to find problems that are new and interesting, but where the amount of background required doesn't take months and months and months to get going. And I feel like this has really helped me hone a skill for kind of finding those kinds of problems. And so it's been crucial for that thread of accessibility in my work. At this point, the last VRM grant has wound down, and I've been doing something else with my summers, and that's the last community I want to tell you about. This is MathPath. It is a national residential summer camp for middle schoolers who love math. And I had been invited for several years to go teach for MathPath, and I kept saying, no, I have undergraduate research students to work with. No, I'm not sure I get along with middle schoolers. Have you met me? And they kept coming back and saying, no, you should give it a shot. These are not your average middle schoolers. They take a qualifying test to get into the program. And while they don't know the definitions or the words in your college classes, if you introduce the structures in an interactive way, they're going to have a blast. And that's been true. I gave it a shot in 2019 to test the waters, and I had so much fun. I've literally taught a class the last 3 summers in counting permutations. So the definitions you saw at the beginning, I've been doing with middle schoolers. I've literally taught a class the last 3 summers in generating functions, which was that complicated formula on the first slide, and they love it. And I love it too, because I keep coming back and doing more stuff, to the point that this past September, I was named executive director of MathPath, which means it's now a year-round project for me, coordinating the people who make the logistics happen for this camp. And you might be wondering, why is this in a research talk? And that's a good question, but I hope you're starting to see the common thread for me as community. And this is contributing to a math community much earlier in the kind of career trajectory, career for middle schoolers, in the pipeline than all these other projects are. It's helping them find a math community at an age where I wish I had had that kind of experience. But even more, I credit MathPath for something really important in the last few years. My MathPath experience has largely coincided with the COVID years. So 2 out of 3 summers I've done it, it's been online. And in the COVID years, I think there's a lot of things that can make you feel discouraged and frustrated and jaded. MathPath is the kind of place where I can have taught something 20 times before, and someone will ask a question that makes me see it from a new angle. So I credit them with keeping my hope and sense of mathematical wonder alive the last couple of years. And I think that very much fits. So those are 3 of the communities that have loomed large in my life in the last decade. And if you want a unifying thread in my work, I think it's the communities. My work is organized around these long-term commitments to helping mathematical communities kind of share love of the field with each other at all different ages. And then my research is kind of the documentation of the fun I'm having along the way. And so that's my MO in a nutshell. But you see there's a few more slides because there's one more loose end for you. I said in the intro that I hoped, especially if you don't consider yourself a mathematician, that I would broaden your view of math in action a little. And I don't know what your default view of math is. I don't know if you were expecting to see something like this at some point, but I'll point out this is the only slide that looked like that. These are 2 actual snippets from 2 of my papers. Sometimes math looks like that. But I want to say if your primary view of math is that it's kind of technical and is indecipherable and lots of computation, I think you're zoomed in too close, because these are really the guts of stories like these. And I hope I've successfully conveyed a sense of what makes these beautiful that you can appreciate even if you don't want to study the guts of these objects. And even more than that, I hope I've conveyed that for me as someone who generates mathematics, this is the content of math. It's about studying structure. But I have a really hard time separating that from the conversations where the structure gets discussed. And so if you want my favorite math in action photos of the last decade, they're these. They all have stories too, but I want to point out one thing in particular. If you look at pictures where I am kind of candid, mid-sentence talking about math and unaware of the camera, the default expression is what you see in these 2. And I would call that one of joy. For me, it really is a joyful activity to think about abstract math objects and wonder why they work as they do and figure that out together with other people. And so I'm fortunate to have a career that's had all these joy-infused activities along the way, make that grammatical. But even more than that, I am really, truly grateful for all the mathematician friends I've made along the way who have welcomed me, encouraged me, invested in me all the way through. That's really what counts in my book. And so for all of you showing up for an hour math talk on a Thursday, thanks for listening. I think you're allowed to ask questions if you want. Shri. Oh, sure. Well, there's multiple structures. Where are they? There they are. So I told you the story of the first three. You want all five or you want the funniest one? What are you hoping for? There's the silliest story behind one of my papers, and it goes with the coins. Would you like to hear the story of the coins? It's the most ridiculous backstory to one of my papers. So one of my best friends from grad school, who had the same thesis advisor as me and was there the same years as me, came to Virum to be one of the summer guest speakers. He did it a few times. And one time when he came to give a talk, it was a beautiful summer day in Valpo. We went for a walk. And as we're walking, he goes, "Do you know those stupid Capital One commercials that say, 'What's in your wallet?' And I saw one on TV last night. So like they still exist." And I said, "Yes." And he said, "I think that's the perfect title for a math paper, but I don't know what math goes in it. What do you think?" And so we actually wrote a paper called "What's in Your Wallet?" We said not everybody spends their coins predictably. There's people like my brother who just take their coins and throw it all in a jar at the end of the day. We should be able to predict the proportions of pennies, nickels, quarters, and dimes in my brother's coin jar. We did our model and we checked and we were pretty on point. But I don't keep my coins in a jar. I like actively try to spend them. And so we tried to make a model based on how Alara spends coins. And even if you're trying to spend your coins, there are 6,720 ways to have at most 99 cents in your wallet when you're trying to spend things down. You only need 100 level math, like what happens in finite math, to analyze it. But you need to make a matrix that has nearly 7,000 rows and nearly 7,000 columns, which means it has 45 million entries. And it's really hard to feed that into the computer. And so programming the computer to be able to handle that was kind of the mathematical adventure. There was a write-up in a Scientific American blog about the paper. It was a lot of fun, but it happened because we were making fun of a Capital One commercial. Yeah. Ken.
Have you ever contributed an integer sequence to the database? How many times?
So if you go to my website, on my list of publications, it says I have been authored, like I have authored, been cited, whatever, in the OEIS this many times. I think it's 364 right now. So a disclaimer there that outside of Rutgers thesis defense committee member for my thesis is the person who founded that database. And when I finished my defense, he said, "You pass as long as you submit every sequence from your thesis to the database." So that was a prereq for me getting my PhD. I'm in there a lot. I thought I heard something else over here.
I was just going to ask if the Scientific American item reported the Capital One commercial.
No, and we actually fought with the journal for whether we got to put an interrobang, like exclamation and question mark, together at the end. And I think they just left it as a question. We really wanted the interrobang. So some of that, yes, some of it is who has the grant support to host people. So for example, if we had had this conference in Valpo in 2020, 2021 was supposed to be in South Korea. And this started off as a much smaller conference about 20 years ago. And it had met in Canada and Florida, and I think New Zealand before I attended. It's just in the last couple virtual years that we've had some attendees from South America. And it tends to be that the people who are in Africa have a hard time affording coming. And so we've had more broad participation doing it virtually for 2 years and are looking at having a virtual component in future years to kind of help with that accessibility. Yeah. Ken.
just want to point out, is you can check if you may have some questions in your
Oh, it could also be just like lots of friends. See, lots of friends. Oh man, the owners of Forefathers are logged in from the brewery. Fantastic. Yeah, and we had an international audience too, because I saw a New Zealand friend in there as well.
looks like you have some patterns here on where the
Oh my goodness, I don't have answers to that.
increasing in the
Something, well, that's also kind of where the coasts are. Any others? I'm so glad you all showed up today. Thanks. I hear there's cake. Are you glad you came?
That was truly inspirational. Thank you.